for the first ever track at vLLM for vLLM at the Ray Summit. So I'm Simon. I'll be sort of the session chair today to introduce you to all the speakers and then also handle Q&A. And so yeah, without further ado, I'm going to get started. Our first talk is going to be from Zhuohan and Kuntai, who are both at UC Berkeley, a part of the original vLLM team, who started this project last year. And this will be a very special talk, given that previously we have been all doing sort of just quick updates. What have we done in the last 2 months? But for this talk, Zhuohan and Kuntai will take us through the history of vLLM, what have we done in the last year, as well as what's going to be happening next year. So yeah, Zhuohan, take it away.
Hello everyone. Welcome to the first talk of the Ray Summit vLLM track. And today, Kuntai and I will be talking about what happened in the past year of vLLM and what are we going to do next. And yeah, let's get started. So vLLM's goal is to build the fastest and easiest to use open source LLM inference and serving engine. And vLLM's original story can actually be dated back all the way to August 2022. So back then, we were serving an OPT 175 billion model. And as a demo, and this is used as a demo for one of our previous research projects. And we found that this demo was super slow. So we started to think, okay, LLM inference can be an interesting field. And we started to build an open source library for LLM serving. And this was actually before the ChatGPT coming out. And so while building this library, we found that the previous systems actually manages the now called KV cache memory very poorly. So we iterate multiple times and converge to the page attention idea. And we started to work on the idea and eventually submitted the paper in April. And meanwhile, vLLM is also used to power the Vicuna demo and the chatbot arena. So, and they are the first actual production deployment of vLLM. And then we we submitted the paper in April, and then we spent another 2 months to polishing the repo to make it open source ready. And we actually open sourced the project in June 2023. So back then, serving LLM is very expensive, and vLLM delivers the best cost. So very fortunately, we got a lot of attractions from the very beginning. And vLLM has continued to grow rapidly with the help of community. And today, vLLM is the most popular open source LLM serving engine in the world. And vLLM has a pretty simple and nice end user API. So first, if you are, say, an NLP researcher and you want to start an LLM in your Python script, you can use the LLM class in vLLM, which is a Python interface for offline batched inference. So you can simply create an LLM object and with the model name, and then you can call the generate method to efficiently run inference on a batch of requests. Also, you can call the new LLM.chat interface to chat with a instruction-tuned LLM. And also, vLLM is a fully serving engine, fully capable serving engine. So you can also start vLLM as an OpenAI API compatible server with a single command. Then you can reuse any kind of OpenAI client by simply replacing the URL to the new URL you just started, the server on. And yeah, today I will do a review on vLLM's progress and main features developed in the past year, which includes the following 6 aspects. So we will talk about model support, hardware support, model performance, engine features, distributed system architecture, and in the end, open source community. And after this one year review, I will hand over to Kuntai to talk about our future plan and also our Q4 roadmap. And yeah, let's get started with model support. So nowadays, we have a very broad support of model support in vLLM. And we started from transformer-like LLMs, for example, Llama. And then we gradually added many different kinds of other large language models. So most noticeably, we first added a mixture of expert models like Mixtral. And then we also added many multimodal large language models like Lava. And right now, we are also actively exploring other kinds of models, like state space models. And also, we are exploring other uses of language models, like embedding models and also reward models. And one thing to highlight is that vLLM supports almost all open source LLMs and vision language models nowadays. And we are very proud to be actually the launching partner of many open source models with the model providers. For example, for Llama, we are actually an official launching partner with Llama 3.1 and Llama 3.2, and we have the official support on these two models on day one. And also, we have many models in vLLM repo that are directly contributed from the model creators. So for example, the Pixtral model and the Q1 to VL model, they are all directly contributed from the model producer. So we can have a high confidence of the correctness of these models. Yeah, and that's about our model support. And next, we will talk about the hardware support. So vLLM started with NVIDIA GPUs because of its broad popularity. But another major stream of our project is to support diverse accelerators. So vLLM currently supports 7 different types of accelerators. So while our primary focus is on NVIDIA GPUs, we are also actively collaborating with other hardware vendors to provide various competitive options to the users. So right now, we also support AMD GPU, AWS Neuron, and x86 CPU, Intel CPU, Google TPU, and Intel Gaudi. So you may ask, how did we manage these all different types of hardware? So our approach is to use PyTorch as a narrow waist. So we use PyTorch as a general abstraction for the model codes and also many other utilities, hardware-specific utilities for different hardwares. And then we utilize the PyTorch generality to generalize our support to different hardwares. Yeah, and next I will talk about model performance. So model performance is always one of our most important priority of vLLM. We want our model to run fast and efficient. So first, from the lowest level, we have a lot of deeply optimized CUDA kernels for all of the different operators within a large language model. So for example, for matrix multiplication, and we have a Catalyst kernel to optimize the quantized matrix multiplication. And also for MOE layers, we have special optimized the Triton kernels to optimize the performance of MOE layers. And for communication, especially all-reduce, we have a custom all-reduce kernel, CUDA all-reduce kernel to optimize the communication performance. And also starting from day one, we have a special kernel for our attention operator. We started from our own page attention operator, and now we have actually adopted many other Catalyst-based kernels, and also all kinds of different attention kernels, including flash attention, Xformers, and also actually flash infer from University of Washington. And for many other layers, for example, like rope layers, we also do have some customized optimized CUDA kernel. And also, we are actively utilizing torch.compile to compile these operators to make the model runs faster. So after we actually implemented a lot of the CUDA kernel optimization, the model runs faster and faster. And we started to figure out that, OK, Python and PyTorch overhead actually start to be a major bottleneck of the model execution. So from our measurement, if we don't do any optimization, we can see Python and PyTorch overhead can take up to 50% of the overall latency. So in other words, so CPU is too slow to launching kernels, and GPU is always waiting for CPU to finish launching kernels to start, and GPU is always waiting for work. So that's why we introduced this CUDA graph optimization. So we can actually, with CUDA graph, we can record all of the kernel launching sequences within a model execution, so that in the next step, we can just launch this CUDA graph once. So there will be no other CPU overhead, and the model will and the GPU will execute all of the kernels all at once. So this way, we can eliminate the Python overhead on the model side, so we can get a better performance. And also, as the model becomes bigger and bigger, quantization becomes more and more important feature. So this is actually our quantization support plan in 2023. So our goal back then is to support a wide range of quantization methods. So basically, we have a 3-step plan. Our first step is to develop a general abstraction for diverse quantization methods. And step 2 is to implement these diverse quantization methods. And step 3 is to optimize the performance of these quantized ops. And right now, I'm very happy to report that we have a wide range of support of almost all most popular quantization methods, including FP8, int8, and GPTQ, AWQ, and B10 bytes. And also, we have many efficient, optimized quantized kernels in vLLM, such as Marlin. Also, special shout out to NeuroMagic on this effort. And also, we would like to highlight that we actually have another new project called LLM Compressor Toolkit under vLLM project. That is a library that can help you quantize the model so that it can, with all different kinds of quantization methods. So you can efficiently quantize this model into a format that vLLM can understand. And so you can use basically you can quantize your model in your own favorite quantization methods and to get the best performance out of vLLM. Yeah, and that's a brief summary. That's a brief recap of what we did on the model performance side in vLLM. And also, we did a lot one layer above the model, we did a lot of also other optimizations and also added a lot of features in vLLM engine to make the models run better and support more different kinds of functionalities. So first optimization we did in vLLM engine is trunked preview. So we would like to thank Amy, the author of trunk preview, and also Sam Bin from Anyscale for implementing this. So what did the trunk preview do? Imagine you have a very, very long prompt. Then if you process this very long prompt all at once, then this prompt will block all of the other ongoing requests. So your user will get a sudden jump on the latency and on the TPOT. So what trunk preview do is that you can actually chunk this very, very long prompt into smaller chunks, and you can process these smaller chunks one by one. And also, while you are processing these smaller chunks, you can also batch this smaller chunk with the previous existing running requests together. So the existing running request latency will not be affected that much. So here with chunk preview, we can see that we can get a 2x performance latency drop compared to without chunk preview, and the user can get a both higher throughput and also a lower execution latency drop. And next is speculative decoding. So for speculative decoding, the goal here is while running a large language model is very, very slow, and we are thinking whether we can use a smaller model to predict what the large model is doing, and then it will use a small model to accelerate the execution of large models. So for example, for this small model, we can use this small model to auto-regressively sequentially generate a candidate, and then we can feed candidate sequence, and we can feed this candidate sequence or this draft sequence to the large model, and then the large model can process this draft sequence all in parallel, so it can utilize the underlying hardware GPU, parallel hardware GPU, and then the large model can verify whether these output tokens are correct or not. So if they are all correct, then we can directly generate 4 tokens all at once, and then generate another, and also generate another token. So we can use these small models to propose draft tokens, and then use large models to verify the draft tokens. In this case, large models can have a larger batch size, can also batch more tokens together, so it can have a better reduced latency, and also reduce the latency of generating very long sequences of large models. Yeah, I think, yes, so this is a large community effort led by Kate from Anyscale and also Lily from UC Berkeley. And I think one thing we would like to highlight from this speculative decoding effort is that this actually doesn't end as an engineering feature. We also have a great research project out of this speculative decoding. So the motivation here is that when we are trying to add speculative decoding into vLLM, we found that actually the vLLM does continuous batching. So when your system load is very high, then the vLLM can already batch a lot of requests. In this case, if you still do a lot of speculative decoding, it won't help your performance. So ideally, what you want to do is that when the system load is low, then you have a lot of extra compute, then you want to do a lot of extra speculative decoding to reduce your latency. But when your system load is high, you want to reduce the number of speculative decoding tokens you do, and even you just don't do speculative decoding to maximize the throughput. And this research is about how can we optimally decide, okay, when should we do more speculative decoding and when should we do less speculative decoding. So if you are interested, feel free to take a look at the paper and to learn more. And next feature I would like to highlight is our hash-based automatic prefix caching. So one example is that, say, for all of the LLM service, typically people write a long system prompt to describe the behavior of this model. So for example, here we have 2 requests sharing the whole system prompt. Then actually the KV cache and all of the computation of this KV cache of the system prompt can be cached and can be shared between these 2 requests. And another example is multi-round conversation. So say you finish 1 round of conversation, and when you start the second round of your conversation, actually your first round, the KV cache of your first round conversation can be cached in the memory, and then on the second round, you can directly reuse the first round of the KV cache, and you don't need to redo the computation again. Okay, so in vLLM, we implemented a hash-based automatic prefix caching method. So what we do is that, say, for an example request, a chat between a curious user. So we will actually give each of its KV blocks a hash. So here, right now, we assume the KV block size is 2. So for block A, we have a chat. Block B, we have represent tokens of between A, and block C, so on. So we will give each block a hash of its prefix tokens. So for example, block A will have the hash of a chat, and block B will have a hash of a chat between A, and so on. So each block will have a unique ID that is based on its prefix hash. And so if we have another request coming in, say a chat between a cute puppy, then we can reuse the first 2 blocks. So because they have the same hash, and for the third block, because it's a different hash, we'll have a different block. So we implemented this hash-based prefix caching method in vLLM, and that is how we do the prefix caching in vLLM. And also multi-LoRa serving. So we in vLLM we supported multiple LoRa adapters can be loaded to vLLM on the fly. And the requests to different LoRa's can also be batched together. And we want to shout out to the S-LoRa authors and Punica authors and Anyscale for the contribution of this feature. And I think one big user ask is for structured output and tool use in vLLM. And right now in vLLM, we actually have OpenAI compatibility for the JSON output format, which is one highlighted feature from OpenAI recently. And also we have extensive integrations with all different kinds of structured decoding and guided decoding frameworks. For example, like outlines, LMFE, and AICI. Also, recently we added ability to use tool calling template. And and also I think as a besides of these LLM features directly related to LLM, we want to also vLLM to be a production-ready serving engine. So we added a lot of metrics that you can directly observe to see whether your vLLM instance is running correctly or not in your production environment. So right now we can use monitor vLLM in real time using say for example tools like Grafana. You can check all different kinds of serving engines metrics and to see whether your engine is running healthily or not. And that's for the engine features. And next, I will briefly talk about our distributed system architecture. So one thing is that vLLM handles distributed inference for you. So from day 1, we actually start to support tensor parallelism. But even just supporting tensor parallelism, we found it's actually can become pretty buggy when you have multiple GPUs and especially have multiple nodes. And so there are a lot of we actually fix a lot of bugs related to communication, and we have a debugging guide for handling and crashing in vLLM. And and also recently we added support for pipeline parallelism, and we shout out to Murali from SendML and also Snowflake for this effort. So starting from v0.5.1, and vLLM will start to support pipeline parallelism. And this is actually best suited for larger models spanning across multiple nodes and have low bandwidth connection. And we recently also added a cute feature to offload your part of your waste to CPU. So if you really, really want to run a very big model on a small GPU, then you can offload part of your waste to CPU to actually execute the model. So although this can be much slower than directly like running on a full bigger GPU, but it's still like if you only have a limited resource, this can help you actually run the model. And also, like one thing we learned recently is that, so we did a lot of optimizations on GPU, and actually we find out like to fully utilize on the GPU, you actually need to pay close attention to everything that is happening on the CPU. So GPUs can be very, very fast, but CPUs are often not. So we actually, in our latest blog post, we did a lot of optimization to minimize the CPU overhead. And these optimization techniques include multi-step scheduling, async output processing, efficient API server, and also zero-MQ-based entry point. So feel free to take a look at our blog post to learn more about these recent system architecture optimizations. And lastly, I would like to highlight this 1 year of like open source community, the development on that part. So we would like to always want to make sure our contributors and users can easily start to use vLLM and start to develop vLLM. So if you want to use the latest release, you can actually simply install vLLM as a pipeline package with pip install, and also you can directly use vLLM Docker from Docker Hub. And also we have a pre-commit. Every commit will come with its Docker images and wheels for like with the latest bug fixes. And also we recently added a small feature that if you only want to develop it on top of vLLM without touching the kernels, you run this command to start to do Python-only development. So you don't need to compile the CUDA kernels, and you can develop much, much faster. And also, like we added a CI/CD for all of the tests, all of the commits we have, and every commit is now fully tested with thousands of tests. And we would especially want to shout out to Kevin Liu from AnyScale for maintaining this CI/CD. And also we want to thank all of our compute sponsors, which can sponsor our very expensive GPU-based CI/CD pipeline. And also we recently added performance checking, since performance is so important, and everyone is saying they are faster than vLLM. So we would like to make sure that, and we would like to make sure that this is, we would like to keep track our performance and have confidence of ourselves. So we actually set it up performance, actually thanks to Kuntai, performance benchmark checking. So you can go to this website and see the performance of every commit and see whether your commit is giving you a performance regression or not. And one thing we want to say is that vLLM is always owned and driven by community. So we would like happy to announce that we are actually in the process of joining the Linux Foundation. And also we host meetups every 2 months. And also we have office hours every 2 weeks. So if you are interested in vLLM, beside of this event, and you can also feel free to participate in all these events to help us. And most importantly, we would like to thank our contributors. So we would like to thank to our more than 560 contributors who have raised issues, participated in discussions, and submitted PRs. And I would like to especially shout out to these 20 committers of vLLM. They are actually the people who actually review your PRs and also make sure like they pass tests and spend a lot of their efforts on maintaining the vLLM project. And yeah, I would like to a round of applause for this. Okay. I think one thing I would like to really highlight of vLLM is that we have a lot of, we are a true community project. So first, from the left-hand figure is the absolute number of the major PRs of vLLM happens every month. So we can see that there are more than 200 PRs being merged every month. And also, like on the right-hand side, actually the percentage of the contributors, where does the contributor come from? You can see that at the beginning, okay, most of the PRs are from UC Berkeley. But like to today, like actually a lot of the PRs are actually not from the UC Berkeley and from like a lot of like active community members from different companies. So we are really happy, and I think it's pretty rare to see that this project has grown into a true community project. And yeah, about adopters, yeah, I think it's actually pretty hard for an open source project to check, okay, who is actually using the project, because you can just keep install and use, and we will actually never know. But I think, fortunately, we are still getting a lot of like queries, and a lot of people are telling us that they are actually using vLLM, and that's also always makes us very excited, and makes us want to continue to work on this great project. And I think one thing to highlight from these adopters is that we have actually been productionized on many clouds, including the major clouds, AWS SageMaker, Azure's AI Studio, and Google Cloud's Vertex AI Model Garden. And also, we are also the default template for the run pod. And yeah, and lastly, I would like to thank all of our sponsors. And we mentioned that our CI/CD has a great cost because it's running on GPU, and it's all possible because of our sponsors who sponsors us funding and compute. Yeah, and yeah, that's all for the recap part. And next, I would like to hand over to Kuntai to talk about what will happen next for vLLM in the coming quarter and coming years. Thanks.
Yeah. Hi, everyone. I'm Kuntai, and I'm going to talk to you about the path forward for vLLM. And there's a QR code on the top right corner of the screen. Feel free to scan it. And there will be a GitHub issue, and we are always open for feedbacks. OK, so let's briefly talk about the Q4 roadmap of vLLM. So in Q4, vLLM will continue adding support to various types of models, including the vision language models and state space models. And also, we will add API so that people can add reward models into vLLM in the future. And hardware-wise, vLLM will keep improving the performance on various hardware platforms like NVIDIA H200 and MI300X. We'll also work on the page attention kernel on Inferentia and a series of enhancements on TPU. And we'll also upstream the Intel Gaudi soon. Performance-wise, we aim to turn on chunk refill and prefix caching on by default. Also, we will make structured decoding faster and fuse communications to reduce the overhead. We will keep on enhancing the batched inference performance and do more kernel optimizations. Production-wise, we will support KV cache offloading to CPU so that you have larger KV cache space. And we will also support KV cache transfer, which is good for disaggregate prefilling. Also, we will adjust the caching policy and the scheduler for a higher cache hit rate. And we'll also ship a series of scheduled spec decoding optimizations. And vLLM is also going through a major re-architecture, but rest assured it will be fast. So we will develop a vLLM engine v2, which includes async scheduling and a prefix caching-centric design. I will talk about them very soon. And we also implemented Torch Compile, full support of it, so that you can optimize your models. And also we have new memory manager for multimodality. And last, we want to focus that we are always there to support our OSS community. We will further working on the performance benchmark enhancement and also a better development doc for contribution and research. OK, so this is the first rearc item, which is asynchronous scheduling. So basically, it's scheduling the next step while executing the current step. It results in a much less GPU idle time because GPU can immediately start executing the next step after finishing the current step. So to make a contrast, before, we will execute the step and then schedule the step, which is this scheduling and execution are piped sequentially. But after the rearc, it will be a more asynchronous architecture where the scheduling happens while the execution is happening, so that we have a much less GPU idle time. And also, we are also using prefix caching to simplify vLLM. So this is because in the current vLLM, there's a very complicated logic to handle parallel sampling or preemption. And in the future, we will use prefix caching to automatically identify reusable KV caches in the parallel sampling or preemption scenario so that we don't need to handle them by ourselves. To make a contrast, before the scheduler directly talked to the parallel sampling and preemption and prefix caching, and now, after that, the scheduler will directly talk to the prefix caching module, and the parallel sampling, KV cache reusing opportunities, and also for preemption will be identified automatically by the prefix caching module. And also, we are working on a rearc that we'll rearc the memory allocator for different types of KV caches. This is because we're observing a very severe GPU memory waste due to incompatible KV cache size. So take the new Llama model as an example. The text, it has KV cache for all layers, but the image, it only has KV caches for 1/4 of the layer. And we are actually allocating memory for all layers, so there's a memory waste there. And the ongoing part is that we will have a new memory allocator that can handle different shapes of tensors with ease. The key idea is that we will first partition the GPU memory into pages with a larger size, and then further partition each large page into different sizes to handle different KV cache size. So we have an illustrative figure here. Basically, we'll have two levels of page tables. The first level will have a larger page size, which is 6 kilobytes in this example. And then we will have a more fine-grained level 1 block memory allocator for different KV cache shapes. Okay, and we will also enable full support for torch compile. Currently, vLLM is manually optimizing on the most popular models, for example, customized CUDA kernels and buffer reusing for Llama models. And our ongoing effort will use the torch compile to optimize all models so that your customized models and architectures will run much faster. And this will also enable new research opportunities. To make a contrast, before, the current vLLM will deeply optimize on the most popular models and left some of the models unoptimized. And after that, all of the models will be deeply optimized by torch compile down to the CUDA kernel level. And we will also ship even better speculative decoding. So the current speculative decoding is still great, but when the QPS is high, it may hurt performance. And what's coming soon is that we will include a dynamic speculative decoding that makes sure the speculative decoding always makes vLLM faster. To make a contrast, the current vLLM, the speculative decoding will be better until the QPS is really high, but after that, the speculative decoding will always be better, regardless of the workload. And we will also store more KV caches into CPU, so that you will have more KV caches for your multi-round conversation and also for your system prompts. This is because the current vLLM only stores KV caches in GPU, and ongoing effort is we will offload the KV caches auto into CPU, and you can even part vLLM with KV cache database like LM cache and Redis for even more KV cache storage. To make a contrast, before, vLLM will only store KV cache on GPU for future reuse, but now you can store your KV cache in GPU, CPU, and even optionally, you can store it in a remote database. And also, this will be the last feature, yeah. And also, the last feature will be disaggregated prefilling, and this is doing prefilling and decoding on different GPUs. So we are going to support it because of several reasons. First, it allows us to configure the parallelization strategy for prefill and decode separately, and also it will result in a much lower tail inter-token latency, and there's no need to configure any hyperparameters compared to chunk prefill, of course. And there will be this will be the best use case when you have multiple types of GPUs. And before, the prefill and decode are running simultaneously on the GPU, but after that, each GPU will only do either prefill or decode. Okay, so let me reiterate. Our goal is to build the fastest and easiest to use open source LLM inference and serving engine. And we are confident that we are on the right track. And now we are ready for questions. Yeah, thank you.
All right. So while the next speaker is setting up, if you have any questions, we'll take probably 1 or 2 quick questions here. And overall, we'll be around in the track as well. So any questions, comments?
Thanks for the great talk. I have a question about having our own mostly my question is around the scheduling. So I know there's a scheduler inside vLLM that can do either based on priority or based on first in, first out. But imagine for business use case, we will have maybe more complicated scheduling logic. Maybe it will based on customer or maybe based on query ID. What is the easy way for vLLM to support such thing? Would it be easy for vLLM to expose some interface that people can port their own schedule logic, or will easier that vLLM implement this by vLLM itself?
Yeah, I think that's a very good question. I think that's also one goal of our re-architecture. So we want to make sure that the scheduler interface is clean so people can easily plug in their own scheduler. I think at the high level, that is the answer to your question, but we are also actively working on that interface, so stay tuned and we will have more updates on that part.
Eventually, it will be an interface that people can implement their own like scheduling logic.
Yeah, I think at the beginning it should be something like just a scheduler class or something like that instead of like direct like user interface. But we will eventually make it more modular and customizable.
All right. Thank you for the good question. If I have more question, please we'll take it offline given the time constraint. And thank you so much for joining the first talk. And then now we'll set up the second talk.
Okay. Thank you.
Yeah, thank you, everyone. Again.